Okay, so let's do just a little bit of recap and then we will build up on that. So the main things I would like you to remember, there are a few things. There are actually, we have, in the end, we have not covered that many concepts. There are not that many concepts in thermodynamics. It's all basically the same thing stated in different manners. So the thing that you need to remember is the entropy change for an adiabatic reversible process. How much is that going to be? 0, right? That's Callan's postulate. It's not going to be. Now, if it is not adiabatic, however, it is reversible. So that means some heat has been exchanged. Let's say delta Q by delta Q is the amount of heat exchange. Then we know in this case, delta S ds is equal to delta Q reversible by temperature, right? How did we see this? We wrote down du, right? This really followed. So both of these statements are equivalent to Callan's postulates. The first one just says that adiabatic change entropy is 0, there exists such a function. And second one is a direct consequence of the monotonicity property. If we had not been able to write down the energy the way we did, we won't be able to write it. So they're equivalent. Let's go one step further. Let's say it is some generic process. Maybe it's adiabatic, maybe it's reversible, I don't know, some generic process. In that case, ds is going to be delta Q by T if the generic process is spontaneous. And that's what we are going to focus our attention on starting now on. So, and if the opposite is true, if ds is less than delta Q by temperature, then opposite or the backward direction is spontaneous. So to put this all in more intuitive terms, let's think about a chemical reaction that is happening A plus B going to C. If this is happening in closed insulated container, and if this is happening in a closed insulated container, and you find that SC minus SA minus SB is more than 0, what would that mean? That would mean the forward direction is positive, right? Forward direction is spontaneous. So forward reaction is spontaneous. And just to remember, spontaneous has nothing to do with time. It just means it will happen. Yeah, go ahead.
So the two processes for the entropy where one is greater than, one is less than, they're both generic or general processes that are spontaneous. They're just
so this is we will see in this context of this example it will become clear. Okay,
so they're both just processes where you don't know adiabatic or reversible.
Some generic process.
You just know they're opposite.
Okay. So if this is true, then the forward process is spontaneous. If SC minus SA minus SB is negative, then backward process is spontaneous. Backward reaction is spontaneous. What do I mean by that? I mean that you will see that C is changing to A plus B, while in the first case, A plus B is changing to C. Now, if the reaction was, if the container was not insulated and you were giving some heat to it, then you would be able to use these two equations to calculate which way will the reaction proceed, right? So if you were giving some heat into it, you will measure the amount of heat that you gave, and it doesn't even have to be reversible. General case, you would measure if SC minus SA minus SB is more than the delta Q by T that you gave to the system. That means that the reaction will proceed in this forward direction. And if SC minus SA minus SB is less than delta Q by T for this particular process, and you have to remember here that it's delta Q is not a property of the system. Delta Q is a property of the process, right? It's path dependent. So depending on what you're doing, it's going to change. It's delta, it's Q given to the system. Just one second, Patrick. It's Q given to the system, but depending on what path you're taking, it could be different. Yeah, go ahead.
So what are the individual SA, SB, and SCs?
Yeah, so entropy is a state function, right? So that's a good question. It means that if you let at that, if C was to reach equilibrium on its own, then you would be able to calculate an entropy for C. Okay. So in this case, C would be going to A plus B. So hopefully this gave you some intuition. Now the problem here is, so let's again look at these four. The first one is, and I want to write one more thing. I want to write one more equation over here, that ds system plus, should I write it over there? No, I'll write it on the next page. Sorry. And that kind of, I'm sure this pamphlet that Nathan and I, who else got this? It's going to be in your exam.
Yeah, you're shutting it off.
It's okay. I'm sure it talks about entropy. So this is very relevant that we should talk about this today. So also, if you listen to the song that I posted on Slack by MC Hawking, known as Entropy, there also he makes this point that creationists always use this argument that the entropy, let's try to beat the creationist argument. We cannot prove it wrong, but well, I mean, we have to be careful as scientists. So we cannot really prove that the earth was not created or the life was not created, but we can show that that argument is wrong. Okay. That's, so if we look at these two relations, the generic one, okay, and now think about, and so we know that ds more than delta q by t is spontaneous for irrespective of the pathway, right? Whether it's irreversible, whatever is happening, doesn't matter. So now imagine a closed system. And the best way to think about a closed system is to think of a system in which something is going on, which might be open, and then think of its surroundings. If you think of system and surrounding together, then they are always a closed system, right? So if you think of a system and surrounding together, then what is the delta Q for that together? That's 0, right? Because it's insulated. So another way of looking at this equation is that ds system plus ds surrounding is more than 0, right? So the creationist argument is that since the entropy of the earth seems to be decreasing, therefore we have some garbage going on, it's violation of second law of thermodynamics, but what you're forgetting is that there is a surrounding. You have to think about that, right? And that's why that argument breaks down. So these are all different ways of writing the second law of thermodynamics. They're all useful, but not exactly. One reason they are not useful is because, just like Patrick asked, what is this S? It's hard to calculate S for a given thing, right? I don't know, how much is Vanessa's entropy today? I don't know, what's the unit of entropy? It's dq is equal to TdS, right? So at least we know the unit of Vanessa's entropy. It's Joule divided by Kelvin, right? So Vanessa, how much do you think is your entropy today? 1000 Joule by Kelvin? Some number, right? We have no way of measuring it. Entropy is hard to measure. I don't think there is a single instrument that can measure entropy. There are instruments to measure heat that have existed for a very, very long time. There are instruments to measure work done on a system, right? Those two things are tangible. So we want to take these conditions for spontaneity and express it in a term that we can actually calculate. That's what we are going to do next. So, and this is so important that I will write it down once again. So far we have seen that spontaneity is, one condition is that ds total, which is equal to ds system plus ds surrounding, is positive, right? This is one condition. Another condition is that ds system is more than delta Q system by temperature, right? That was Clausius inequality. So these two we have seen. So my question for you is it possible to write down the condition for spontaneity only in terms of state functions of the system? We can do that in very limited case, right? If it's adiabatic reversible process, we can do that. And perhaps we cannot do it in the most generic case. But can we do it in fairly generic settings? So we will just show next that if the process is happening at constant temperature and volume, okay, then there exists a state function known as A, such that dA system less than 0 is the condition for spontaneity. And it doesn't matter whether the process that is happening at constant T on V is adiabatic or reversible or irreversible. So this is like the most useful thing we have seen in thermodynamics so far. This is something you can directly go and use in your lab or your theory or whatever you do. It's super useful. And I will define A in a moment. And then we will show that there also exists a state function known as G, such that dG system, and I will normally not write system or surrounding. When I don't write it, I assume it's system, okay? But just to clarify here, that this has nothing to do with the surrounding. This is a property purely of the system. At constant temperature and pressure, these four are conditions for spontaneity.
Can you just, sorry,
Yeah.
can you repeat the last, like where did you arrive? How did you arrive at those last two conditions?
I didn't arrive, I'm telling you the answer. We will arrive.
No, but like what's the logic to just write those two statements?
There's no logic. I'm showing you the destination. Now I will show you the logic. Okay, this is the result we are going to prove. So when I was very young, I tried to be a mathematician, and it was a disaster because my real analysis professor, he had just come back from Princeton after his PhD, and he was teaching undergrads for the first time. So he went to the blackboard and he writes THM theorem, okay? And he looks at us, scratches his head and goes, I don't remember the theorem, but I remember the proof. Then he leaves certain line and then he goes, PM, proof. It fills up 5 blackboards. And he goes, oh yeah, now I remember the theorem. I'm done. So no, but the point here is that there exists state functions which have this property, okay? And this should seem mystical to you. Why do these things exist? And now we will see what they are and why this is true. This A is known as Helmholtz free energy. Some books just call it Helmholtz energy. I call it Helmholtz free energy. And it is defined as E minus TS, energy minus temperature multiplied by entropy, while G is known as Gibbs free energy. And that is equal to G equal to H minus TS. So today we are going to derive these things from a very practical viewpoint. In a couple of lectures, we will see how these things are actually all Legendre transforms of entropy of S of NVE and how they come from there. First, we will do it from a very practical standpoint, which I do even in the undergrad PChem. So, but we will go through it quickly. So what I'm going to show you here is that if you were to calculate this A, and if a process was happening at constant temperature and volume, so then this condition is the condition for spontaneity. So let's look why that is the case, okay? So that's the theorem. Now let's look at the proof. So we want to show that D of E minus TS, where everything is for the system, okay? There is no surrounding, less than 0, is the condition for spontaneity, is condition for spontaneity at constant temperature volume. So if you had a reaction, and now I can't really use the symbol A, if you had a reaction going from X to Y, and if you could calculate the Helmholtz free energy for Y, and if you could calculate the Helmholtz free energy for X, and if this reaction was happening at constant temperature and volume, which is a reaction in a closed test tube, right? So that's why it's very important. If you could calculate the Helmholtz free energy of the product and of the reactant, it will go in the direction in which the Helmholtz free energy is decreasing. Okay, let's try to prove this. So to prove this, we will start with Clausius inequality. We'll start with ds more than delta Q by temperature, right? This is generic. Clausius inequality is as generic as it's going to be. Nothing adiabatic, nothing reversible. We are talking about constant temperature and volume process. At constant volume, what can we replace delta Q with? Delta E. Everyone remembers their first law of thermodynamics, right? Because delta E is equal to delta Q minus PdV, right? And we are not worrying about additional work. So dV is 0, constant volume, right? So delta Q is equal to dE. So let's call this as, I started numbering equations. Let's call this as equation number 1. Let's call this as equation number 2. Therefore, 1 plus 2 imply ds is, and I don't have to write delta E for E because it's a state function, so I can write dE. So ds more than dE by T is condition for spontaneity at constant volume. I have not yet introduced constant temperature, okay? Now think about this function that I introduced, A, E minus Ts. So what can I say for D of A is equal to D of E minus Ts? That is going to be dE minus TdS minus SdT. Now, if I assume constant temperature, this is going to be dE minus TdS, right, at constant temperature. Let's call this equation number 3. Equation number 4, and let's call this equation number 3. Therefore, dE is equal to dA plus TdS, right? This is also 4. So let's put 4 in 3. So we get the condition for spontaneity. 3 is telling us that TdS is more than dE, right? And what is dE? We just showed that dE is dA plus TdS. Therefore, dA less than 0 at constant temperature and volume is the condition for spontaneity. Okay? So this is just 2 lines of algebra, but it becomes so useful, so powerful. Instead of thinking about path functions, if you have a constant temperature and volume process, you can just measure the change in Helmholtz free energy, which you have to take my word is way easier than if I ask Vanessa what's her Helmholtz free energy today, I don't think she would still have an answer. It's complicated, but you can measure it, right? By doing calorimetry, by measuring change in energy, by measuring heat and things like that. It's more tractable than the entropy. Okay? Yeah.
Why do we ignore other forms of work? Chemical work, for example. Like if this is a reaction, how can we ignore?
You can keep it here. It will just show up in the end. It won't matter. It will just dangle everywhere.
So where will it show up?
It will show up in, so you will have a work definition over here. I have to think, remind me on Slack, okay? I think it just shows up and then doesn't matter, but maybe I'm wrong. So remind me on Slack, okay? Yeah, I mean, otherwise it would be less useful, right? Because in the chemical reaction, we will have Dn, right? We will have mu Dn type terms. So I think it stays to the very end. And my guess is that it shows up on both sides of this equation, and that's why it does not matter. But we can think about that later. Or if one of you already manages to think, then please, I first want you to think more, okay? And post a solution on Slack. Okay, work through it. Either you reach a contradiction or you solve the problem. Either way, post it. Okay, so we have just showed that at constant temperature and volume, dA negative is the condition for spontaneity, which is equivalent to Clausius inequality, at least if there is no additional work. If there is additional work, then we have to be careful. So I know for G, I have definitely, for the next one that I'm going to show, I have definitely worked on it with additional work, and it does not matter. So I'm hopeful here also it does not matter. So, okay, and where we defined A as internal energy minus T minus S. So you can see a hint of why Legendre transforms might be showing up, because look at this A, how is it defined? A minus, what was the definition of T in terms of entropy? It was partial S by partial E at constant NV S, right? So a very peculiar form is here, right? It's not just, you can see it's very interesting. There is E minus derivative of the other thing divided by the derivative of the first thing. So this form will keep showing up again and again, and later we will see why. So we just showed that dA less than 0. This one we just showed. Are you happy now, Vedant?
I'm still not clear as to why you defined it as E minus TS. I like that proof is fine with me.
It's the proof. The later why we defined it this way, that will come from Legendre. Right now it's
not mathematically. Why would you suddenly?
because I show you it works. This is proof by construction.
That's fine. I'm just saying that you have these conditions for spontaneity.
Yeah.
Why would you suddenly want to define these additional?
Because
terms?
this is, are you a theorist or an experimentalist?
Experiment.
Then you should know constant temperature and volume are settings which are quite common in experiments. Constant temperature and pressure are settings which are quite common in experiment.
I get that.
Once you get that, then I'm showing you this by construction.
But you could construct any function that does this for you. And how can you
Really?
say-
Show
No,
me
no.
any function,
I'm
any other
not-
function.
I'm just, okay, that might be a harder thing to do, but I'm saying that you've not disproved that you can't have another function that. you
Sure,
can
I'm not,
say.
I have not disproved it. Sure,
You're saying
that's
for this
the,
constant,
I'm, there could be a Vedant. Every time new Vedant function comes up, Vedant is equal to something minus something, which also does this. I'm not claiming anything about a uniqueness. I'm telling you this will do this. Okay? In thermodynamics, we don't worry too much about uniqueness. At least in this level of thermodynamics. Okay, there could be other functions, but when we get to Laurent transforms, you will see why this is unique.
and you still can't make absolute measurements for these things, right? Because again, you don't know what entropy is, or.
Well, that's why I'm talking about D of A.
Right, that gives you an idea of the net spontaneity of the.
What do you mean net
I
spontaneity?
mean,
There
of
is
the
only
spontaneity,
spontaneity.
sorry.
That's it. What do you want then? Spontaneity is about change. Which direction is change measured in? So differential showing up is natural. You never care about A. You only care about dA. Okay? What will you do with A? It's always about change in A. Yeah, go ahead.
So when you measure DA,
Uh-huh.
you're not measuring E or T or S.
No, you're measuring change in E or T or S.
Well, what I'm saying is, you said, didn't we start by doing this because you said it's hard to measure entropy?
It's hard to measure entropy. It's equally hard to measure change in entropy, but it's easy to measure change in energy.
Right. So we don't, when we measure,
Yeah. This so far I have not showed you yet as to why is it easy to measure A. Right, you're correct, because E is easy. There is still the entropy dangling, right?
I'm just saying, when we measure A, we measure A directly. We don't measure E and then S and then.
So far, I haven't shown you how you will measure A. In the end, I will show you how it connects to the heat capacity, which is something directly measurable.
Okay.
Okay, that's where it will come from. What we have been able to do so far is to measure, is to write down the condition for spontaneity, which is change in terms of change of a state function. Okay, so you should not be worried about, well, you didn't tell me anything about A. Thermodynamics is all about change. Okay, it's look at all our relations. Everything is in terms of D and delta, right? D this, delta that. So it's all about change. Let's keep moving from here. Let's write, and here it showed up because I knew the answer, so I could show you it fits the bill. So it's natural for Vedant or anyone else to wonder as to why could there not have been some other function which did the same thing, right? It's natural to wonder that. When we get Laurent transform, you will see this function is unique. Yeah, go ahead.
Quick question. So does only, in order for the reaction to be spontaneous, does only one of these need to be true?
Depends on the condition, right?
Okay,
This is most generic.
right,
This implies this at constant temperature and volume.
okay.
This implies this at constant temperature and pressure.
So then here's a follow-up question.
Yeah.
Just thinking back to like, Jack and
Mhm.
and stuff. I can think of situations where we've had delta S be greater than 0,
Mhm.
but not delta A and delta G.
Sure, because it's not a constant temperature volume process.
I think that can be possible if the mu factor comes in. I'm wondering if that may make a difference.
Maybe, but most of the confusions in PChem happen because condition for spontaneity, and I know even professors will get confused in this, you have to be careful about which condition are you checking it in, right? So the invoking G does not make any sense if it's not a constant temperature pressure process. Invoking A does not make any sense if it's not a constant. So you find your contradiction and show me.
Okay.
Okay, and it's possible that the mu type term or the additional word that we ignored does some issue. Okay, it's possible. Let's go to G. And here, once again, I'm showing you these things by construction. If you did not know how to find this, you wouldn't be able to succeed. But turns out when we do Laurent transforms, you will see why these things are unique. Okay, so now we want to show, good, yeah, keep the questions coming. We want to show next that dG less than 0 is condition for spontaneity at constant temperature and pressure. So same type idea. We will start with ds more than delta Q by T. That's generic. At constant pressure, what is delta Q? D of H. This is pop quiz from last time, right? Delta Q is equal to dH. Therefore, ds more at constant P. So therefore, ds more than dH by T at constant pressure. So now let's think about dg, which we have already defined. dg is equal to d of h minus ts is equal to dh minus tds minus s dt, or dg is equal to dh minus tds at constant temperature. So now we assume the other thing also, that it is constant pressure. We first assume, now we assume constant temperature. And if we equate both of these, we get, so again, one more line. So this tells us that dh is equal to dg plus tds. So put this dh over here. What do we get? We get ds more than dg by t plus ds, or dg by t is less than 0, or dg by t, or dg is negative, because in thermodynamics, in infinite system size limit, we know temperature is always positive, right? That was our monotonicity condition at constant pressure and temperature. Could there be other state functions that have the same property? So far, we have not proved it. That's why we need Lagrange transforms, and you will see why this is unique. So now we have more state functions that can get the job done. And my claim at this point is without proof, is that these G's are easier to manipulate than just entropy. Definitely, you don't have to worry about the heat that is being given to the system. It's purely a state function of the system, right? So it's easy to manipulate. And this is also the other reason why these things are very nice is because, can anyone tell me why expressing the condition for spontaneity purely in terms of state functions is very, very useful?
It doesn't depend on what reaction or what.
Yeah, it's awesome because it just doesn't matter how you get there, right? So in drug design, which is one of the fields my group works in, this leads to a method known as free energy perturbation. People do something known as alchemical transformations. You have to change one drug molecule to another drug molecule. You can do bizarre things that have nothing to do with reality. You have half an oxygen, third of a chlorine, who cares? As long as the end products are the same, right? And that's why it's very powerful, because it's purely state function. You can take whatever path you want, just doesn't matter. Even more important, you have an organic chemistry reaction going on with 50 different pathways, right? You just don't care what are the pathways, right? If you have taken any orgochemistry, which is currently very infamous in some New York Times article, maybe some of you have seen it, right? And that's why organic chemistry is hard, right? There's 50 different pathways going from A to B. This is telling you, if you're just interested in whether the final product can be formed or not, ignore all the pathways. Just measure the A for the product and measure the A for the reactant, and we'll get it done. Instead, if you were using Clausius inequality, you would have to look at it for every single pathway, and that's going to be a mess, right? So that's why this is so profound, because it just doesn't matter. You don't even have to do the actual reaction. You can do with water. Okay, and we have some unanswered questions. Number one, why shouldn't there be another state function with this property? Number two, are we being very careful with the chemical potential and additional work? Those two we will answer offline. Well, the first one we will answer later. The second one we will answer offline. Anything else?
In an actual experiment, how easy is it to control, or just, so you're measuring A and G because you can't measure entropy, but how
No, so far I haven't showed you how we measure A and G. So far I have showed you that if we wrote something in terms of entropy, we would always have to deal with the irritating delta Q on the right hand side, right? So now that has disappeared. Essentially what we have done is to absorb this inside entropy and show that in constant temperature volume, constant temperature pressure, it is free energy. It is just a state function. How to measure this, I haven't shown you yet.
But here you have to be very careful with regards to the surrounding entropy. Like you're taking everything from DS system.
Not in these two relations. You don't have to worry about surrounding at all.
And I'm saying if you're actually doing an experiment, it's not related to this. It's slightly a off-topic question. You're starting off everywhere from DS system is greater than. It'll work. Your relation will still hold because you have total entropy greater than dq by t. But you have to be careful about the measurement you make for the surrounding entropy also. Right?
Again, if you use these equations,
You don't have.
it becomes wonderful. And one of the reasons, and I can tell you why it becomes practical, and we will do it probably later, or I will just give it in the homework, is an equation known as Gibbs-Helmholtz equation. Gibbs-Helmholtz equation is actually super powerful. What it does is to express delta G in terms of delta H. And now it becomes very easy because delta H can be measured by measuring heat capacity, right? So if you have a funky reaction happening through some complicated pathway and you want the delta G for that, you can express the delta G in terms of delta H for the reactant and the product. Does not matter what pathway are you taking. Once again, now you have totally forgotten what pathway you were taking. All you need to do is to measure the change in heat capacities of the initial product. So we look at Gibbs-Helmholtz equation. That's what makes it very, very useful. And yeah, and that is the whole idea here, that you don't have to be worrying about the entropy of the surrounding. In this one, you will have to be careful how you're calculating entropy. In this one, not. Okay. So we'll keep building on this, and everything will demystify. But now we are ready to do something which, well, all of you have been waiting for Lagrange transforms, but even before that, you have all probably been waiting for Maxwell relations, which is like the nemesis of undergrad thermo. But hopefully after this, you will see why it's really simple and you never need to remember it. You can derive it in 2 lines, because I never remember it. Okay, it always takes 1 minute to derive it, any Maxwell relation. And we will see what they are. So the first question we have to ask, so you can see already, is there anyone that disagrees that G is equal to H minus Ts and A is equal to E minus Ts are state functions? Is anyone here who thinks that these are not state functions? Why are they state functions? Because it's a sum or product of state functions, right? Everything is a state function. T is a property of T as well. T is not a state function, but it really is, right? It's a variable used to define the state. H and S are state functions, right? So everything is a state function here. So G and A are also state functions. So the natural question is, do they have natural variables? Also, enthalpy. We did not ever think about natural variables for enthalpy, right? So far we know that the natural variables for entropy are NVE. We know that the natural variables for energy are NVS. The question is, what are the natural variables for H? What are the natural variables for A? What are the natural variables for G, right? How would a thermodynamically complete relation look for DH and DA and DG? Okay, so let's do that. We'll start with G. And it's just going to be some very boring and simple algebra, but it will fall out immediately. So we know, so natural variables for G. So we know G is equal to H minus Ts, right? H minus Ts. DG is equal to DH minus TDS minus SDT. Does it help? Do we see natural variables here? We don't. I mean, we can talk about H, but it's not quite clear, right? What's going on? So now let's think about H. Anyone remembers the formula for H? E plus PV, right? So that is D of E plus PV minus TDS minus SDT. Let's write this down further. DE plus PDV plus VDP. Looks like we are doing, like Alice in Wonderland, going down the rabbit hole further and further, just adding more and more derivatives. What can we do now? Again, let's not worry about additional work for now. We can write down DE, right? What is DE? TDS. It's a state function, right? Remember, DE is always TDS minus PDV. It's delta Q, which is not always TDS. That's where you have to be careful, okay? DE is equal to TDS minus PDV plus PDV plus VDP minus TDS minus SDT, and few things cancel out. Plus TDS minus TDS cancels. Minus PDV plus PDV cancel. And we are left with DG is equal to VDP minus SDT. And once Omar goes home and checks, you will find that essentially, if you wanted to worry about number, it will just show up over here. It just dangles. It really doesn't matter. It's boring, it's bookkeeping. We could keep it all the time, but it wouldn't matter. So now you can.
Sorry.
Yeah.
Is it a reversible process that we're working on? Or
We
we're
are talking only about state functions. So there is no process here.
So I've forgotten, but when is D just equal, DQ just equal to TDS? I thought we defined it only for a.
But I didn't use that.
No, for the.
dE is equal to TdS minus PdV plus mu dN. That is
Yeah,
straight from the Bhagavad Gita. It's always true. What is not always true is whether delta Q is equal to TdS or not. These two are two different things.
Sorry.
No, this is important. Just don't be sorry. This is confusing. This
No.
can happen.
I
D.
thought we derived the D relation from DQ.
No, this came from the fundamental property,
Yeah.
right? So when we do undergrad thermo, this is a bit complicated because it's kind of convoluted. But if you believe in Callan, then this is a direct consequence of the monotonicity property that something like this can be written. In fact, this is how we define temperature. That's like ground truth, right? That's where we start. Yeah, go ahead, Sophia.
Where did the mu
Or just short of nowhere. Literally. So what I said is for now, there is no mu dn, right? But if I wanted to write mu dn, what I would do is to add over here. Yeah, it will keep showing up. So this will be in your homework, don't worry, to deal with all the mu dns and convince yourself that it just pops up in the very end. Okay? Huh? Omar has a head start. So we have just shown now that what are the natural variables for G? Pressure, temperature, and number. Why? Because look at the differential over here, d of p, d of t. And if you don't want to worry about number, you can ignore it. Without number, it is g of pt. Okay. So, and you could have anticipated this from what I wrote about the spontaneity condition. I said that dg is negative is the condition for spontaneity at constant pressure and temperature. So you already had hints that this is going to be true. Okay, so the natural variables for G are P, T, N. Now this is very, very important, and irrespective of if you stay in science, most likely you will be using something like this. Yeah, go ahead.
How is G one of the natural variables P if it's constant in P and T? And that just mean that only N is G?
Well, I'm not talking about anything constant over here. There is no mention of anything constant in this page. Right?
That's how we derived this.
No, you said when for a system with constant temperature and pressure, you have a DG less than 0 is the condition. for
They are two
stability.
different statements.
Okay,
Yeah, there are two different statements. G is a state function, which is H minus Ts, whose natural variables are pressure, temperature, and number. So if you're doing an experiment at constant pressure and temperature, and you are changing from one reactant to some other product, you will measure the G and see whether the G increased or decreased. Okay, and that will give you an answer of what's going on. So what I was blabbering before that is that when you're looking at an experiment, you have to be very careful in looking at what are the control variables. Okay, if the control variables are P, T, N, then you will always think in terms of G to define spontaneity. If the control variables are something else, you will think in terms of something else. And this will happen. You will see this sooner or later, that you will be reading a paper and people have been sloppy about this. Their control variables were actually volume, temperature, and number, and they used Gibbs energy. I see these papers all the time. And if I'm a reviewer, then I just don't even review it. Like, this is wrong. Send it back. You know, because it happens more often than not, because thermodynamics tends to get ignored. Yeah.
How I may have missed the argument, but natural variables are one for which the function, if defined in those variables, gives you complete thermodynamic information.
Yeah.
Right? Where in this argument are we able to say that we get all the thermodynamic?
Because this is equivalent to this equation. Right? This equation was thermodynamically complete.
Okay.
And you can go back and forth. We were just able to derive dg is equal to vdp minus sdt plus mu dn from this equation. But you could do the opposite thing. So they are interchangeable. They are exactly same. That's the idea. Okay? There is nothing missing because they are exactly same. Okay? And mu dn, I will always keep dangling at the end. I will not write it. And all you have to do is to go and write, basically in the H formula over here, you have to write mu n, and then everything works out, and you will do it in homework. But you have to take my word for now that mu dn just shows up over here. If you're not happy, you can just ignore it. And in fact, just work with G of PT. Okay? Yeah, go ahead.
So I know we represent pressure as a partial, right? And we said we couldn't do that for energy. We couldn't represent partial derivatives as the natural variables. Why can we do that here?
It depends on what function. Like,
What are you measuring? So here pressure is being measured.
Okay,
Here pressure is being measured. Here is not a derived quantity. That's the whole idea. So if pressure is being measured, if temperature is being measured, they are the natural variables for G. Okay. So let's look at this different derivative. dG is equal to VdP minus SdT. This equation does not have a name, but is actually a super powerful equation. You will be seeing sooner or later an exercise problem, which you will use this to do things that you could not think were possible, this simple equation. But we can do something else with this equation. First of all, what does it tell us about partial G by partial P at constant temperature? It's V, right? Everyone sees that? What does it tell us about partial G by partial T at constant pressure? Minus S. Next class or so, we will use these arguments to explain why is it that as we increase the temperature, solid goes to liquid, goes to gas, and not the other way around, right? So it's already quite useful. We can do something else, which is a bit non-trivial. And that you have to remember a bit of your calculus. If a function of xy, some generic function of xy, can be written in the following form: df is equal to h of xy multiplied by dx plus g of xy multiplied by dy, then there is a condition on h and g. Anyone remembers that condition? And the name for that condition?
it's the Euler
Yeah.
relation.
Euler relation says that partial h by partial y at constant x must be equal to partial g by partial x at constant y. Otherwise, it won't be true. Otherwise, it won't be a total derivative. So this is Euler's condition for existence of a total derivative. Okay. If this is confusing you, the best way to brush up on this is actually Khan's Academy. Go and Google Khan's Academy, Euler's condition, total derivative. You will find nice videos of Salman Khan explaining it to you, not to be confused with the Bollywood actor. He's laughing. Yeah, you don't want that guy explaining Euler's. It would not be good. So, and so this means, I can write it down over here. For example, if you have x squared dx plus y squared dy, does it follow that property? It does. Trivially, right? Because both derivatives are zero. So you could have a function for which this is true. But now think about x cubed cos of y dy dx plus y to the power 4 hyperbolic tan of x dy. I just made it up, but I'm almost certain that if you differentiate this with respect to y and if you differentiate this with respect to x, they won't be the same thing, right? So there cannot exist a function for which this is true. Okay, this is what it is saying. So it's super powerful. Yeah,
Sorry.
you're curious today. It's good.
For the, you said that we're going from E plus the fundamental equation to this thing. Can you generalize that statement? So we start with any equation that's in terms of its natural variable.
And if you can interconvert, then they are also
So
natural.
any function
Yeah,
that
yeah,
will
yeah,
always
Yeah,
be.
that's what we are going to do next. So, but now let's apply, and I should number equations. So we have, this one is called equation 4, this one is called equation 5, and let's call this Euler condition as equation 6. Okay? I'll write it down over here because we are going to do it again and again. So if f of x, if b of f of xy is equal to h of xy dx plus g of xy dy, then partial h by partial y at constant x is equal to partial g by partial x at constant y. A simple way of remembering this is that when you take the double derivative of f, the order does not matter. That's what it's really telling you. Okay, when you did d2f by dx square, it won't matter which thing did you differentiate first, which you have used probably many times. Okay, and this is what we use when we do multivariable calculus, multivariable integration. We switch the order of integration, right? That's what you're using over there. So let's use equation 6 in equation 4, which is dg in equation 4. So just to remind you, equation 4, which is dg is equal to vdp minus sdt. That was equation 4. And equation 6 is over there. So let's do that. What will we get? We will get partial v by partial temperature at constant p is equal to minus partial s by partial p at constant temperature. This is equation 7, and this is Maxwell relation. I will call it Maxwell relation number 1. It's not that it's number 1 in any way, it's just one of them. It's so bizarre. You would have never expected such a relation to hold true, right? Change in volume with temperature at constant pressure is change in entropy with pressure at constant temperature. It shows out of nowhere and it's super powerful. Okay. And again, don't try to remember this. Their internet is full of mnemonics to help you remember Maxwell's relations. Okay. They will have these magic squares and things like that where the arrows are going in funky ways. And then you spend all your time trying to remember which way is the arrow going. So it's kind of stupid. Okay. So don't do that. What you need to remember is the formula for G. If you remember the formula for G, and if you remember this most important equation, D is equal to TdS minus PdV, you can derive dG is equal to VdP minus SdT. Once you derive dG is equal to VdP minus SdT, you need to remember your Euler's equation, and you will get your Maxwell relation. So we have shown natural variables for G. Next, we are going to show natural variables for E. Let's just do E and derive the Maxwell relation for E. Okay. So for E, we already know the natural variable, that is dE is equal to TdS minus PdV, and I'm going to ignore the n term for now, okay, because really it's just bookkeeping. So what are the natural variables for E? S and V, right? We are ignoring n for now. So from this, we can see that partial E by partial S at constant V is equal to temperature. We already know this. This is how we define temperature. And partial E by partial volume at constant entropy is equal to minus pressure, correct? Now let's derive the Maxwell relation for this one.
Where is that even multiplied by volume? Or is that?
Oh, it's constant. It's my elephant handwriting. Sorry. Now let's do Maxwell relation. This thing differentiated with respect to this thing at constant this thing. Okay. And I hope today video is working. Otherwise, it will be like, yeah, what is this thing? Who knows? So therefore, partial T by partial volume at constant entropy is equal to partial minus P, so minus partial P by partial S at constant volume. Okay. This is equation number 8, and we call it Maxwell relation number 2.
Why can we always say that if you can possibly have a function that's like that second function you wrote up there? Why is that always correct?
Which function?
The second one, you said that's not going to equal to Euler.
This thing?
Yeah. There's not even the one on the very bottom.
This one?
Yeah, so we're deriving the Maxwell relations based on that, right?
No, this is not possible.
That's what I'm saying. So say we have a function for those partial derivatives. Why do we always say that's true? So what if
What
we
do you mean?
had?
This was account. This is an example which is never going to be true. It doesn't exist. Such a function can't be true.
Okay.
That was the point.
Okay.
That you cannot find an f for which that would be true. You simply cannot. Because if you did, then that f would depend on x and y. It would be a state function, and it's not possible. Because so state functions follow Euler's relation. That's another way of thinking about it.
So that relation is to hold both ways. That's an argument you're making here.
So we got our second Maxwell relation, and good luck trying to remember this. It's like same symbols with random minus signs, you know, you will forget it. Don't try it. Don't even try the mnemonics. There will be at least one in-class exam in this course, and I will let you have a cheat sheet, okay? You will, cheat sheet means a sheet in which you can write down whatever. Now, don't stretch it, okay? Has anyone played that game called Twister? You stand on a sheet, you know, and you will do like this, and it's a big sheet. Don't make your cheat sheet like a big, like bed sheet or something, okay? Like a normal sheet on which whatever you want to write. A normal, what do I mean? This size, maybe a bit smaller, maybe a bit bigger, I don't care. Just don't bring like a big, you know, like a banner. So you won't have to remember things, okay? But you can still derive it. It doesn't take much time. So we did E, we did G. Which one should we do next? Which one do we have left? A and H. Let's do H. What was the definition for H? E plus PV, right? So let's start. So DH is equal to DE plus PDV plus VDP. What is DE? TDS minus PDV plus PDV plus VDP. And you cancel minus PDV plus PDV, and you're left with DH is equal to TDS plus VDP. Okay. I'll write it down on the next page. So once again, so H was E plus PV. So DH is equal to DE plus PDV plus VDP. DE is equal to TDS minus PDV plus PDV plus VDP. These two cancel out. You are left with DH is equal to TDS plus VDP. And again, at the cost of really pissing off Sophia, I can add a plus mu dn over here. You have to take my word, it just comes up, okay? But we are ignoring that over here. It just dangles, it's this kind of harmless spectator. So what are the natural variables for H? S, P, and N. They're kind of bizarre, okay? But there are many processes where this is the natural thing to think about. My wife is a geologist over here, and she studies volcanoes. And apparently volcanoes, many times when a volcano is exploding, entropy, pressure, and number are the natural variables you can control. And so she cares about enthalpy deeply. In our home, we don't argue over thermodynamics, by the way, because we both think that we are experts. And we realized when we started dating, it's not a good idea to argue over thermodynamics. It's my dating advice to you. If you're dating an academic, don't discuss thermodynamics at home. So we have TDH. Now let's do our, so we can do two types of things now, right? First, we can talk about just the partial derivative. So let's call this as equation number 9. So partial H by partial S at constant pressure. And again, if I had to be very careful, it would be constant pressure and number, right? So constant pressure and number is equal to T, right? Partial H by partial P at constant S and N is equal to V. And what about the Maxwell relation? That will be partial T by partial P at constant S is equal to partial V by partial S at constant P, correct? That's our Maxwell relation number 3. Okay, and again, once again, don't try to remember it, but just remember the gist of it. However, even though I say don't remember it, the art sometimes comes from when you're solving thermodynamics problems, it's not clear which Maxwell relation will help. And you need to be able to have them handy to see which one will help. If you try to keep deriving them, you'll get stuck. So in your cheat sheet, I do recommend writing down Maxwell relations when it goes to the in-class exam. Okay. You can derive them, it took 1 minute, but it's if you have it in front of you, it's useful. Okay, now let's do the final one. A, Helmholtz energy, right? So A was, what was the definition of A? Hmm? So dA is equal to dE minus TdS minus SdT. Once again, dE is equal to TdS minus PdV minus TdS minus SdT. And one thing I want to do is make sure I have numbered these equations. So this was, yeah, today is the type of class that if you showed it to like some organic chemist or inorganic chemist, just the notes, they would be like, this is why I never did PChem. But it's not that hard, right? It's really simple. It's really, really, really simple. It's the closest thing I can think of. It's like sheet music, right? If you just look at sheet music, which I don't know how to read, it looks very complicated, right? There's all these troubles and all those things. But if you know what it is, it means something, right? And you can express it. It's just like sheet music. It's a language. It's simple. And it's worth practicing it, becoming comfortable with it, because even though the organic chemists might not like it, this is what they need to describe whether their reaction will happen or not, right? It really matters. Yesterday's Nobel Prize was for click chemistry, where the whole idea was when you do something, the things become very spontaneous. So even the basis of click chemistry is that you can attain spontaneity in a very quick way, in an efficient way. So with this, what do we get? TdS minus TdS here cancel out, and we are left with dA is equal to minus PdV minus SdT. Let's call this as equation number 10. So we can see that partial A by partial B at constant temperature is equal to minus P. Partial A by partial T at constant volume is equal to minus S. And we can derive our Maxwell relation. That will be both have minus over here. So the minus minus cancel out. It becomes partial P by partial T at constant V is equal to partial S by partial V at constant T. And this is Maxwell relation number 4. Okay. Now I'm finally equipped to create really, really difficult algebraic thermo homework exercises for you. It's like the world has now opened up for me to be mean. Okay. Don't try to remember the expressions once again, but remember the gist of what we did. The gist was that if you can interchangeably go from dE is equal to TdS minus PdV plus mu dN to these other equations, then you get a fundamental form for these other state functions. And the differentials over there are the natural variables for that state function, right? That was the idea. And if it can be written down in that form, then we have Euler's relation to extract more useful identities out of it. We haven't put the identities to use yet. We will do it next time to derive the internal pressure for a van der Waals gas. But I want to do one thing before we finish today, is to summarize all fundamental relations. Okay, so these are all fundamental equations. These are not equations of state. So we have today derived GAHE, 4 fundamental equations. Okay, and let's write them down together. And they are all equivalent. That's why the derivatives that show up in them are the natural variables for those particular that particular state function. So the first one is dE is equal to TdS minus PdV plus mu dN. This I hope everyone remembers. The second one, which even I remember, the third and fourth I will forget for sure, is dG is equal to VdP minus SdT plus mu dN. Okay, and I'm just literally putting mu dN, and you can go back and see at home that that's how it works. It just shows up. The third one is dH. What did I have? TdS plus VdP. TdS plus VdP plus mu dN. And the fourth one is dA is equal to minus PdV minus SdT plus mu dN. Okay, these are all fundamental equations. They are all thermodynamically complete. It just depends on what is it that you're controlling in the experiment. If you're doing molecular dynamics simulations, who here has done a molecular dynamics simulation? Okay, let's you tell me. So have you done a molecular dynamics simulation where the box size was changing, or was it fixed volume? So that is constant number, constant volume, and constant temperature. So which state function would you use over there to describe it? Looking at that. dA, right? Constant number, volume, temperature. Are you aware that you can do molecular dynamic simulations where the box size changes? You have heard of it, right? It's known as NPT, where the volume changes. The best way to do it is through an algorithm known as Parinello-Rahman algorithm. Parinello was my postdoc advisor, so it was a lot of fun working with him. He invented it in late 1980 for the first time to do it. So if you're doing an NPT simulation, what would be your state function that you would look at? G, right? What if you are doing a simulation or an experiment in which the number is also changing? And you want to think of mu as a control variable? We haven't derived that yet, right? That leads to yet another function known as the Gibbs potential. We will talk about that later. We haven't done that over here. But there is something interesting over here. From each of these equations, you can write down a formula for mu, which looks very different, but it is the same because it's the same mu everywhere. So mu could be written as partial E by partial N at constant S comma V, or mu could be written as partial G by partial N at constant P comma T, or mu could be written as partial H by partial N at constant S comma P, or mu could be written as partial A by partial N at constant V comma T. And it's the same mu for each of them. This is quite useful that it's the same mu everywhere. You can calculate it from whichever thing you have. Okay, I want to do one more thing. We have some time. It's very quick. I will just show you one use of the Maxwell relation and then we will stop. Okay, this is a dense class. There was a lot of material, but it was important that we cover this. Okay, so let's derive the internal pressure for a van der Waals gas using. Yeah, go ahead.
So if G, H, and A have natural variables that are intensive, doesn't that mean we have to know PE for E?
So that's a very, very good point, and you're really getting to Legendre transform. So think about G. There are two natural variables that are intensive, and one is extensive, right? This is really why we define them. When we do Legendre transforms, that will be the motivation, that intensive variables are easy to measure, right? Temperature is way easier to measure than energy. Pressure is way easier to measure than volume, right? That is why we do it. So it's very helpful. These are way more helpful than anything else. So let's use these Maxwell relations, one of the Maxwell relations, to derive the internal pressure of an ideal gas, and then we will stop. It will take 1 minute. Of a van der Waals gas. So van der Waals gas, what is the equation of state? Is P is equal to nRT. And again, if you forget what is it, just remember ideal gas. So ideal gas is PV is equal to nRT, right? For van der Waals gas, you assume that the things have a certain volume, B. So you get something like this. So that means nRT by V minus NB. And then you say there is an attractive term also, right? And the attractive term goes as square of density. So AN square by V square. So I always forget the formula for van der Waals gas. And this is how I try to think through it. And then I remember what it is. So I want to derive the internal pressure, pi T. Anyone remembers the formula for internal pressure? It was partial E by partial V at constant temperature, right? Not to be confused with the thermodynamic pressure, which was partial E by partial V at constant S and number, right? So this is different. So how do we derive this for a van der Waals gas? In order to do this, we have to go, and this is how a lot of practical thermodynamics works. You are stuck with a relation, you go and stare really, really hard at all the Maxwell relations together and see if one of them does the job. So let me write down all the Maxwell relations on one page. Okay, here, let's summarize them. All Maxwell relations, and then we will stare and see which one works. So we have 4 Maxwell relations, partial P by partial T at constant V is equal to partial S by partial V at constant T. Partial T by partial P at constant S is equal to partial V by partial S at constant P. We have partial V by partial T. So 4 state functions, 4 Maxwell relation. Minus partial S by partial P at constant T. And partial T by partial V at constant S is equal to minus partial T by partial S at constant V. So which Maxwell relation might be useful here? As of now, nothing. We don't see anything, right? Because partial E by partial V at constant temperature does not show up in any of these, right? So we have to do a bit more work. So we are lost. Okay, let's think about when lost. Write down the fundamental equation for any one of them that you know. Okay, I always remember dE, which is TdS minus PdV. Let's start from here. Okay, from this one, what can I say about dE by dV? dE by dV is equal to T ds by dV minus P, correct? I just divided by dV, nothing wrong. Therefore, partial E by partial V at constant temperature is going to be temperature multiplied by partial S by partial V at constant temperature minus pressure. Now, does anyone see which Maxwell relation might be helpful? First one. I just have to stare a little bit, right? And then you see. Stare after some manipulation. That's the formula. So if we use this one over here, what do we get? We get T multiplied by partial P by partial T at constant V minus P. Can we do partial P by partial T at constant V for an van der Waals gas? Yeah, we have this over here, right? So if you differentiate this with respect to temperature at volume, at constant volume, what will be the effect of this term? 0. At constant volume, there is no temperature dependence over here. When you differentiate this one with respect to volume, what will be the effect? Just temperature will go away. It will be nR by V minus NB. So this will be T multiplied by nR by V minus NB minus P. What is that? That is minus AN square by V square. So we have just shown that the internal pressure for a van der Waals gas is minus AN square by V square. No, it's plus N, yeah. So that was kind of neat. And you cannot do this without the Maxwell relation. If you just started with the equation of state, which I learned 2 years ago when I was teaching undergrad thermodynamics, and there was this student, Matt Laskowski, who then figured out that you just can't do it. And the reason you cannot do it without Maxwell relation is because you don't have thermodynamic completeness, right? Information is missing. You cannot derive such a relation. So think about this equation. If I had not given you any of this information, right? I will uncross it. If this was not there, you would probably not know how to proceed, right? How to calculate this. You would be stuck. So how did we do this? When you get stuck, first, write down the Maxwell relations. See, maybe something just works directly and allows you to manipulate it into a form you can use. Here, that was not the case, but we did have a partial E. So we thought about our integrated first and second law, and then we worked from there. So you will have, starting now on, homework problems and midterm and exam problems, which will be of the same flavor. You will have an innocuous looking relationship. You think, I can do this, no problem. And you will get horribly, horribly stuck. Okay. One of them will be the exact relation for CP minus CV. In order to do that. So the next homework will be out on next Tuesday. Okay. And I will have office hour. You will have 7 or 8 days to do it. And depending on how that homework goes, I might or might not change the midterm time. I will see how it goes. I don't want to give midterm too early. I also want to grade your first midterm before I give the second one. Any question about this? Good. We did a lot of algebra today, but it's useful. So next time we will look at dG is equal to VdP minus SdT type things and try to explain as to why is it that you go from solid to liquid to gas? Why does that happen? Which will be next Tuesday.